So, this is our next lecture on interconnect parameters. In that particular interconnect parameters, that is basically unit 2. So, in that we will discuss first what is interconnect, okay, then what are the geometry of the wire. After that we will also see what are the parameters that influence the performance of the IC. Okay. So, we will try to finish with the resistance and the capacitance. So, the wire, as I already told in the previous lecture, that wire is nothing but your interconnect or the net, sometimes it is also called net. Okay. So, basically what is the purpose of this interconnect? The purpose of the interconnect is to transfer the information from one transistor to another transistor, or we can say that it provides a connection between the transistor. Okay. So, basically it carries the information. Okay. That is why it is called a interconnect. Now, why this interconnect plays a major role in the performance of the modern system? As we know that prior to 1990s, that at that time when we are using the aluminum material, at that time the number of transistors in a particular IC is very less and the computation speed is also very low. Okay. So, the performance of the particular integrated circuit was mainly measured with the help of the performance of the gate. We are not concerning much about the interconnect delay, but as we are moving forward year by year, as we are the density of the density of the transistor is getting increased in particular IC, then there is a huge requirement of the wires also. Okay. But scaling the transistor is still giving a better performance, but with the technology update, with the advancement of the technology, the dimension of interconnect is also getting reduced. But as we reduce the dimension of the interconnect, there are huge power dissipation, the delay because of rise in the resistance. Clear, that we have to see. That is why in today's technology we have to take care both the delay of the gate as well as the delay of the interconnect. That is why the overall performance of the IC is depend on not only the gate delay, it also depend on the interconnect delay. That is why we have to understand what are the parasitics that influence the performance of the overall circuit. Clear. So, in the early days the transistor were relatively slow, that I already told you, and at that time the resistance is also very low. Under those circumstances, the wires could be treated as an ideal equipotential node. Okay. And we are only concerned about these lumped capacitance. We are not considering the RC values. Okay. But in the modern VLSI process, the transistor switch much faster. Okay. If it switch much faster, that means the current, the flow of current is higher, right? But due to the lower dimension of the interconnect, it has to face with the higher resistance. If the resistance is higher, the RC delay will exceed the gate delay. Clear. So, moreover the wires are packed very closely together. That means the complexity of this interconnect wire is very close. If the complexity of the wire is very close together, then obviously the coupling capacitance will give a rise to the delay, because it will, if higher capacitance will involve, that means it will take a larger time to charge it. Okay. So, we have to reduce all those things. So, basically the interconnect is first divided into 3 categories based on the length of the wire. So, this is the, you can say, I have taken it from ITRS, okay, where you can say this portion is called local interconnect, where a small length of wire is used to connect, to provide the connection between source, gate and drain, okay, or within the transistor, that you can use a local interconnect. But when you have to connect one blocks to another block, then you have to use a little bit longer wire, that is termed as a interconnect. And to distribute the clock signal, clock at the signal function throughout the entire circuitry, you required a longer wire, okay, or you can say to you provide a VDD or the ground to the entire circuitry, you required a longer wire, that is termed as a global wire. So, basically the interconnect is divided into 3 categories. One is local interconnect, second is intermediate, and the third is global interconnect. Now, how this interconnect looks geometrically, clear. So, the wire we treat it as a rectangular, in a rectangular form like this, clear. So, this is your silicon wafer. On top of the silicon wafer we are having dielectric constant. So, these wires are placed on top of this dielectric constant with which having a particular distance, that is called h, height from bottom of the wire to the ground, okay. And this T is the thickness of the wire, and we are having width, this is the width of the wire. Now, based on the ITRS, the spacing between the two wires should maintain a minimum distance. So, W is equal to S, or it can be 2S, it can be 3S based on the requirement, but it should not be less than S, clear. So, this geometry, the total, if we take the sum of this width and spacing between the wires, then it is termed as a pitch, okay. And if you want to find out the aspect ratio, then you have to take the ratio of this thickness and the width, that is called aspect ratio, okay. Previously in the older technology node, when we are talk about 180 nanometer and above it, at that time the aspect ratio is very much less than 1, but in the modern process we are having aspect ratio almost equal to 2, okay. Now, this is a pictorial representation that you can see, where we are having a different metal layers, okay. So, this portion is your transistor, in which we are having a different metals, and you can also observe that the total area of area, or you can say the dimension of the metal is getting increased, means it is getting thicker. So, metal 1 is having a very small small area, then it is little bit higher, then the thickness is getting increased, clear. So, that you can easily observe. The similar kind of thing you can also observe in the different things. So, based on the technology node, we are having a different level of metals. It can be up to metal 6, it can be up to metal 7, it can be metal 11, okay. So, based on the technology node, we are having a different level. So, this one is for the 90 nanometer technology node, and this one is for the 45 nanometer technology node. So, for 90 nanometer technology node, we are having 6 level of metal layers, and for the 45 we are having 7 levels. Now, so how to perform, how to obtain the or model the performance of the interconnect, that we have to do through this circuitry. So, we have to first convert the interconnect wires into a equivalent lumped model or distributed model, okay. So, we will talk about all those two category one by one. So, in the lumped model of interconnect lines, either if we talk about the old technology, at that time we do not have much higher frequency, but now we are having in the gigahertz frequency. So, currently we have to take the impact of inductance also, but in the older technology we are not concerning about much about this inductance, because the impact of this inductance is very negligible, you can say, for older technology. That is why at that time we are taking only R and C, okay. The delay we are calculating based on the R and C, but for the higher performance circuit, which is having a higher frequency in terms of gigahertz, we have to include the impact of this inductance. So, basically the lumped model is can be designed by mean of 3 different types of model. One is L type, second is pi type, and the third is T type. So, to observe the performance of the circuit, you can opt any one of the model type, okay. Either you can take L type model, pi type, or T type. So, you have flexibility to choose which one gives a better performance and how you are modeling the things, clear. So, this is you can see in the L type model we are having a series resistance with inductance, and then we are having one capacitance, clear. But in the pi type model, what we are doing, we are having a both in series resistance and inductance, but the capacitance are splitted in both terminal. So, we can also say that the overall capacitance that exhibit by that particular dimensional interconnect should not exceed, okay. So, whether you split it 2 times or 3 times, okay, based on the different type of model, because in the L type model we are only having a total capacitance C, but here when the capacitance are split in both the node, then it will be C by 2 C by 2. So, that the total impact will be only C. Similarly, in the T type model, this resistance and inductance are getting splitted. So, the total impact, if you take R by 2 and this R by 2, it is R. So, L by 2 and L by 2, and this capacitor is only C. So, this is the lumped model for 3 different types. Now, we are also having a distributed model. Okay. So, what we are doing, instead of evaluating on the whole wire, what we are doing, we are splitting those longer wire into a small segment, so that the computation time required to compute the output or the performance is little bit lower. Clear. So, in that case, if we are having a L type model, you can see this is my L type model for n segment. If we are having n number of segment, this that does shows we are having n segments. So, for single, if you are having one segment, that then n value will be 1, that means it is R, L and C, that is it. If we are having a 2 segment, then it will be R by 2, L by 2 and C by 2. This again R by 2, L by 2 and C by 2. Clear. Similarly, for pi type model, you have to observe carefully when you are having a distributed circuit for pi type model. At that time, this will be R by n, L by n, but here you are having C by 2 n, okay, C by 2 n. Here also we are having one more capacitor, C by 2 n and C by 2 n, but if you solve both, you will have only C by n. That is why I have written directly C by n, right. Clear. So, be careful while having these values. So, apart from that, the inside, if you take this one, the last one and the first one, suppose if you are doing for 3 segment, then the first one and the last one will be C by n and the rest of the capacitance will be only C. Be careful, because this is a dot dot, that is why I have assumed that this one is the last one and this one is again started. Clear. Now, for the T type model, you can see that this one is splitted. Okay. So, it should be R by 2 n, L by 2 n, again L by 2 n and R by 2 n. So, R by 2 n and R by 2 n will be again, so this is a 2 by n if you write. So, R by n and R by n will get, let me see here, this is. So, we are having 2 resistance and 2 inductance at this point. So, it will have R by 2 n, R by 2 n is equal to R by n. Clear. So, likewise we are having at the source terminal, here we are having R by 2 n, L by 2 n, and at the last we are having R by 2 n and L by 2 n, but rest of this will be only L by n, R by n, L by n, R by n. Clear. If you solve this 2, you will become L by n. Clear. Now, again C by n, all the capacitor will have C by n only, right. So, based on the synopsis H spice, we have also done a comparison, and we have found that what are the difference in performance for different models, okay, that we have done in the synopsis H spice for a length of 2000 micrometer. The interconnect length we have chosen 2000 micrometer for the material, and we have found this for 32 nanometer technology node. We have taken the parameter, physical parameter for 32 nanometer technology node, and we have found what is the delay for that particular circuit. So, we have observed that for L type L model, it is giving 2.46 nanosecond, for T type it is giving 1.65 nanosecond sorry, and for pi type it is giving better performance 1.52 nanosecond. So, from here we can easily say that the pi type model is much better as compared to other model. So, one can adopt pi type model. So, the impact of, so what are the parasitic values that basically influence the performance of the circuit, that we will see one by one. Okay. So, the interconnect parasitics basically reduce the reliability, it affects the performance, and it will consume the power, huge power it will consume. Okay. So, this has been classified in 3 category, one is resistance, second is inductance and the capacitance. Clear? So, what kind of resistance we can see in a different materials? Clear? That we will see. So, if we talk about the nanomaterials, okay, like if we give the example of graphene, currently graphene is having a huge potential that can be used for interconnect application. So, okay. So, that we can see. So, we have to understand what kind of different resistance we are having in particular materials. So, the terminology should know. Okay. So, we are having a line resistance, okay. That means the wire we are having, and that wire exhibits a line resistance. But if we talk about the nanomaterials like graphene, it exhibit a different kind of resistance like scattering resistance, okay. We are having scattering resistance and contact resistance we are having, quantum resistance we are having for the nanomaterials, okay. Similarly, for the inductance, either we are having a magnetic inductance, kinetic inductance, or mutual inductance, okay. Now, in terms of capacitance, we are having a quantum capacitance for nanomaterials and electrostatic capacitance that you can observe between the material and the ground, and the coupling capacitance that you can observe between the two wires, coupling capacitance, mutual coupling capacitance, okay. Now, we will see one by one. So, the first one is the resistance, okay. So, the resistance of a wire, okay, as we know that if we reduce the dimension of the resistance, what will happen? The resistance will increase by mean of this R equal to rho L by A, where area is nothing but width into thickness. This is the total area as we have seen in the geometry of the wire. Clear? So, we have to take care of this resistance. We have to maintain the lower resistance for the wire. So, how we can maintain? Either we can increase the width, okay, or we have to use lower resistivity of the material. Clear? So, these are the different materials that can be used for interconnect application, but that depends on in what particular technology you are using. Clear? Earlier we are using silver, aluminum, okay, but and gold also we have used, but it is very rare material. So, we are not preferring it. Apart from that, we are currently using a copper material because of the availability and better immunity than other materials like aluminum and silver, okay. It is having a better electromigration immune power, okay, and the resistivity is also lower as compared to aluminum. Now, if you take the ratio of this resistivity to the thickness, that you cannot alter while designing the circuitry. So, this is called a sheet resistance, okay. This sheet resistance can be denoted by R square, this R and square. Clear? By using this, you can see this is your ratio of resistivity to the thickness of the material. Clear? So, this is basically R square, it is it's coming R W. So, please rectify it, it is R square, that is equal to resistivity by thickness. Clear? Now, the unit of this R square is ohm per square. This is the unit of your resistivity. Okay. Now, what are the things we can adopt to reduce the impact of this resistance? Okay. So, we are having a different way. First, either we can use a material with a lower resistivity, okay. But currently we are using a copper which is having lower resistance, but even though the copper is having some kind of limitation, you cannot reduce much, you cannot use those copper material for very low technology node, okay, because it has a several you can say challenges while if you flow a high current density current through this conducting wire, it will have electromigration effect. Okay, it means the transportation of material from one place to another place, it will form a void and hillock. Okay. So, the another way is we can reduce the wire length, which is not always possible. For a local interconnect we can use, but for the global interconnect we have a longer resistance. Now, the next is increase width. So, if you increase the width of the wire, R equal to rho L by A is your width into thickness. If you increase the width, what will happen? The total area required to connect to provide the connection between the transistor will be higher. Okay. So, we do not have a choice to increase the width of the wire, clear. So, it will consume more area, and if the area is larger, that means it exhibit a higher capacitance. Like we know that these wires are placed in perpendicular to each other. So, assume that this wire is having higher width. At that time, the total area covered by this will be more. So, the capacitance between this is very high. So, we always prefer that the intersection point should be as much as less, so that the capacitance will not impact much, clear. So, the next is increase the height, but if you increase the height, the fringing capacitance will come into the play, and it will also reduce the performance of the circuit, clear. Or either we can provide a bigger contacts, or you can use a less via, or we can use a metal instead of polysilicon even for shorter distance routing, clear. And we can also use a silicide coating to reduce the polysilicon resistance, because in the local interconnect we mainly using a polysilicon to connect the source to drain kind of thing. Okay. Next is capacitance. So, in the capacitance, as I already mentioned, that we are having a coupling capacitance, we are having fringing capacitance. Okay. So, between this this is my interconnect wires, and this is the ground. So, the isolated wires over the substrate can be modeled as a conductor over a ground plane, clear. The wire capacitance has two major components, one is parallel plate capacitance, okay, and the fringing capacitance. So, this parallel plate capacitance can occur between the wire and the ground, and this fringing capacitance arises from fringing field along the edge of the conductor. Okay. This wire conductor we are having, at the edge we will see this impact, fringing capacitance impact, okay. That also we have to reduce to have a better performance. Now, next is this fringing capacitance is more complicated. If you want to compute the value of this fringing capacitance, it is a little bit it required a huge numerical field solver to find out the exact result. Okay. So, obtaining this fringing capacitance is little bit complicated. So, and the wire adjacent to the second wire on the same layer can exhibit a capacitance to that neighbor. Okay. So, that means if you are having a parallel wire, okay, then you will also face some kind of a capacitance between the wires. So, in general, as we know that the C equal to epsilon 0 A by D, that is in general formula for the capacitance. So, for the classic parallel plate capacitance formula, that you can see here, this one, C equal to epsilon ox divided by H W into length. Okay. And if you want to find out the capacitance, then you can also use this formula for the copper material. So, this is a empirical formula that is computationally efficient and relatively accurate, okay. And is you can use this formula to compute the capacitance. Now, these are we will see what are the factors that basically influence the overall performance. So, the wire delay is proportional to the charging time of the capacitance. So, more the time it will take, more the delay you will have, and more the time that means it will take a higher power to charge the capacitor, clear. Apart from that, there is a coupling capacitance is also increased. So, that increases if we are having a very close proximity, that will give rise to the noise. Okay. So, we have to maintain a lower delay by eliminating all this impact. So, what are the things that we can adopt to eliminate these things? So, first we can use a low K dielectric material. Okay. Second, we can increase the spacing, but that is not always acceptable, because if you increase the spacing between the wire, you will require a higher area. And another way is separate the two signals with a power or ground line. That means you can provide a shielding between the wires. If you provide the shielding between the wires, the interface between the two wires will be lower. We can also use a minimum wire width. Okay, but if you use a minimum wire width, it will increase the resistance. Okay, that also you have to take care, right? So these are the things you have to maintain while implementing a circuit. You have to very careful what are the impact of parasitics, what are the impact of resistance and capacitance and inductance while having a better performance. Okay, thank you.